The second half of this discussion will supplement your knowledge of positive displacement and centrifugal pumps, as required to meet our training objectives. In addition, you will have a small amount of review. You will review the operating principles of positive displacement pumps and how they are classified. You will learn to recognize the different kinds of rotary pumps from cutaway models, photographs, or sketches, and to describe how these pumps operate. From a cutaway model, photograph, or sketch, you will learn to identify the major parts of a diaphragm pump and to tell the functions of these parts. Diaphragm pumps are especially useful in certain services. You will learn what these services are. You will learn more about steam-driven reciprocating pumps than other types of positive displacement pumps because you're likely to operate more of them. You will learn to identify the major parts of the steam end, driver of these pumps, to tell how the parts work and how they are lubricated. You will learn to identify the parts in the power transfer system, how they work, and how they are lubricated. The liquid end, the actual pump, has parts corresponding to those of the steam end. You will learn their names, functions, and lubrication. You will learn that steam-driven reciprocating pumps are classified both by the number of cylinders and by stroke characteristics. You will learn the meaning of such terms as stroke and revolution, and how pump sizes are stated. And you will learn to use this information in solving problems. You will learn to describe and actually to perform start-up and shut-down operations. And you will learn to troubleshoot steam-driven reciprocating pumps. That is, recognize and correct common operating problems. You will learn some of these things in class and some in Skills Lab, actual hands-on practice. You will learn more about centrifugal pumps. You will learn how specific gravity of the liquid being pumped affects pump head and pump horsepower requirements. You will learn to understand and use such terms as brake horsepower, liquid horsepower, pump efficiency, and pump capacity. You will learn more about pump characteristic curves, also called pump performance curves, how to develop them, and how to use them. You will learn why pumps are sometimes operated in parallel, and sometimes in series. You will learn to make certain calculations concerning centrifugal pumps. For example, to calculate liquid horsepower required to pump 100 gallons per minute of water at 200 feet head. You will learn to describe and actually to perform start-up and shut-down operations. You will learn to troubleshoot centrifugal pumps. That is, recognize and correct common operating problems. Now open workbook number 2 to exercise 4. Do you remember the operating principle of positive displacement pumps? A positive displacement pump operates by reducing the volume that a liquid can occupy. This bucket is full of water. The water occupies the entire volume of the bucket. Suppose we drop in this brick. The brick reduces the volume the water can occupy, and some of it overflows. Our brick and bucket are a positive displacement pump. Not very useful, of course, but they illustrate that a positive displacement pump operates by reducing the volume that a liquid can occupy. Some positive displacement pumps are classified as rotary pumps. A rotary pump's moving parts rotate, and in so doing, reduce the volume the liquid can occupy. Rotary pumps are further classified as gear pumps, screw pumps, lobe pumps, and sliding vane pumps. Let's take a closer look at each of these. Here is a standard gear type. When the liquid goes in, it occupies a comparatively large volume. But when the gears mesh, they reduce the volume the liquid can occupy and force it out into the discharge line. Here is an internal gear type. It looks different, but it works the same way as the standard gear type. In this screw pump also, incoming liquid occupies a comparatively large volume. The rotating screw reduces the volume the liquid can occupy and forces it out into the discharge line. As the lobes in a lobe pump rotate, they too reduce the volume the liquid can occupy and force it out into the discharge line. The sliding vane pump works on the same principle. Vanes are mounted on a rotor that is eccentric to the pump casing. As the rotor turns, vanes first slide out to trap a quantity of liquid, then slide in to reduce the volume the liquid can occupy and force it into the discharge line. Let's look at these rotary pumps again. Gear pumps, screw pump, lobe pump, and sliding vane pump. Now open workbook number 2 to exercise 5. The diaphragm pump is a special type of positive displacement pump. In it, the flexing of a diaphragm reduces the volume the liquid can occupy. The diaphragm is flexed by some such device as a cam, lobes, or a plunger. This one has a plunger. When the plunger makes its backstroke, this flexible diaphragm flexes in the same direction, enlarging the hydraulic chamber and creating a vacuum. Suction line pressure forces liquid into the pump through the suction valve. During the backstroke, discharge line pressure keeps the discharge valve closed. The forward stroke of the plunger flexes the diaphragm forward, reducing the volume of the hydraulic chamber. Pressure closes the suction valve, opens the discharge valve, and forces liquid into the discharge line. Let's look at the major parts again. Plunger, diaphragm, hydraulic chamber, suction valve, and discharge valve. Note that the liquid being pumped does not touch any part of the pump that requires lubricating oil. Some liquids must be kept so pure that they cannot stand even minute contamination from traces of lubricating oil. A diaphragm pump is a good choice for pumping such liquids. A diaphragm pump is also a good choice for pumping corrosive liquids. Liquid does not touch and therefore cannot corrode most of the pump parts. Only the diaphragm, valves, and liquid chamber need to be protected against corrosion. Now open workbook number 2 and complete exercise 6.